What time is it is a question, so it's not a proposition. And then D was 2 to the n is greater than or equal to 100. Again, that is not a proposition because we don't know what n is. Okay, so the answer was B for that one. The moon is made of cheese. The next question, which of the following statements is true? And were given a bunch of propositions. Okay. Right. Okay. So as which of the following statements is true? The first statement was a conjunction, 1 plus 1 equals 2, and 2 plus 3 equals 4. So you have to remember when the statements are true and when they're false. Conjunctions are only true when both parts are true. 2 plus 3 equals 4 is false, so it's false. The next B was 2 plus 3 is 4, or 1 plus 1 is 3. Both of those are false, so it's false. The third one was a conditional statement. It said if 1 plus 1 is 3, then 2 plus 2 is 5. There, the hypothesis is false, and the conclusion is false, so the statement is true. So C is true. D was a biconditional. It was 0 is greater than or equal to 1, if and only if 2 is greater than or equal to 1. One of those statements is true, one of them is false. So different truth values, the biconditional statement is false. Okay. The third question was, which of the following is the converse of the statement, if I study, then I do not fail the exam? So converse, we switch them. So it would be, if I do not fail the exam, then I study, right? Sometimes the grammar is a little weird, but that would be the converse. Which of the following is true if the domain for all variables consists of all real numbers? So for that one, the one that was true was the last one. There exists an x such that x squared equals 2, right? There is a real number x such that x squared equals 2. It's the square root of 2. The others were false. And one was there exists an x such that x squared equals -1. That's false because x would have to be the square root of -1. That's not a real number. Okay. Then there was the statement for all x squared plus 2 is less than or equal to 1. That's not true.
We can't see your screen.
Can be greater than 1. Yep.
Professor, we can't see your screen.
Yes, I'm aware. Okay. And let's fix that. Okay. The screen should now be visible. Okay, great. Okay. So we were going over this one. Which one of the following is true if the domain for all variables consists of all real numbers? Okay. There exists an x such that x squared equals -1. That's false. X would have to be the square root of -1, which is not a real number. B, for all x squared plus 2 is less than or equal to 1. That's false. X squared plus 2 can be greater than 1. Okay. For C, for all x squared is not equal to x. That's false. X squared can equal x if x is 0 or 1. So the only one left is D. All right. And 5, is the following statement true or false? So I gave you a statement there, and I said, is that thing a tautology? That's true. That is a tautology. If you do a truth table for it, you'll see that it's always true. Okay. All right. So that was the quiz. Let me now see what questions you guys had. Okay. Okay. All right. So if you want, I can scroll back if you want to take a look at anything. Number 4. Yeah, sure. There's number 4 right there. Okay. Number 4. All right. Let's go over number 4. One moment. And number 2. Sure. Okay. So number 2 was this one here. All right. So let's start with number 2, and we'll do that, and then we'll do number 4. Okay. 3, 2, and 1. All right. Let me switch to our whiteboard here. One moment. Okay. Okay. So number 2 again, the question was, which of the following statements is true? Okay. The first A was a conjunction, so it was, right, which of the following is true? The first was a conjunction, so you were given the statement 1 plus 1 is 2 and 2 plus 3 is 4. Okay, so for that to be true, both statements have to be true, but this statement is false, right? So if one of them is false, the statement is false. Okay. The second was a disjunction. It was the statement 2 plus 3 is 4, or 1 plus 1 is 3. Okay. For a disjunction to be true, at least one of the statements has to be true, but here both are false statements, so it's false. Okay. Next was a conditional statement. It was if 1 plus 1 is 3, then 2 plus 2 is 5. Okay. So here our hypothesis is false and the conclusion is false. All right, so if they're both false, then it's a true statement. Okay. Remember, conditional statements are only false when the hypothesis is true, but the conclusion is false. And finally, the last one, D, was a biconditional. It was the statement 0 is greater than or equal to 1, if and only if 2 is greater than or equal to 1. Okay. So here, the two statements have different truth values. One is false and one is true. Biconditionals are only true when the two statements have the same truth value. So that statement is false. So the answer was C. Okay. Let's see. 2 is greater than or equal to 1, right? It is one of those options. 2 is either greater than or equal to 1. So that's a true statement. Okay. All right, let's move on to question 4. Let's go over 4 one more time. So question 4 was, which of the following is true? Okay. If the domain consists of all real numbers, so you were given a couple of options. Your first option was there exists an x such that x squared equals -1. For that to be true, x would have to be equal to the square root of -1. That's not real, okay? So that's a false statement. There is no real number x such that x squared equals -1. Okay. The next option was for all x squared plus 2 is less than or equal to 1. Okay, that's false, right? If I let x equal to 2, let's say, okay, 2 squared plus 1 would be 5, which is greater than 1, okay? So this statement is also false. Your next option, option C, is the statement for all x squared is not equal to x. Okay, that's also false if x is 0 or x is 1. They'll be equal. That's false. Okay. And option D was there exists an x such that x squared equals 2. Okay, which is true. Just let x equal to the square root of 2. That's a real number. Right, that's a real number. So that's true. Okay, so your answer would be D. Okay. Okay. Any other questions on that? Okay. Scroll up? Yeah, sure. Okay. Let's pick up where we were last time then, unless there's any other questions. I'm going to be giving you homework after today's class, all right? Okay. Yes, the square root of any positive, or the square root of any non-negative number, of any positive number or something that's, or zero is real, okay? The only thing that's not real is the square root of a negative number. Okay. Can we go over number 5? For number 5, you just make a truth table, all right? And all the values should come out as true. Okay. 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 If you want to see number 5, you can send me an email and we'll send me an email and we'll do it together. What if the square root is 0? That's real. The square root of 0 is 0. 0 is a real number. Okay. Is there class next Monday? I don't think so. I'm going to have to check the schedule. Okay. I think so. I think so. I'll double check the calendar. I suggest you do the same. Tuesday might be a Monday schedule. Okay. All right, I'll have to double check the calendar on that. Okay. Okay. All right. So let's continue where we were last time. Okay. So, all right. Let's just maybe quickly go over one of the last things we were discussing last time. Okay. So we were discussing translating sentences. Okay. So I gave you this expression here in logic. This is for all x, c of x, or there exists a y such that c of y and f of x comma y. Okay. So you were asked to translate this into English, where c of x was the propositional function of, one moment. Yeah, where c of x was the propositional function x has a computer, and f of x comma y was the propositional function x and y are friends. All right, the domain was all students in your school. Okay. So the way you translate these things is you go step by step. Okay, this is what we were discussing last time. So if I start at the beginning here, I start with for all x. Okay, what's my domain? The domain for the variables are the students in the school. So for every x, x is a student. For every student x in your school, okay, that's for all x. Now I move on to the next part. C of x. What is C of x? That's the statement x has a computer, right? That was told to us. Then I have a disjunction, so I write down or. Then I have there exists a student y, or there is a student y in your school, such that c of y and f of x comma y. So y has a computer, and x and y are friends. Okay, so this is what the sentence is if we go piece by piece. Okay, the only thing is when we're writing a sentence and we're asked to translate it into English, we were saying last time we have to write it as a regular normal English sentence. So it's got to sound like a normal sentence. It can't have variables floating around in it. Okay, so we have to sort of take a moment, read what we've written, and try and understand what it's saying. Okay, So if we read this thing, it's saying, let's read over it again. It says, for every student X in your school, every single student in your school, X has a computer. So every student in your school has a computer, or there is a student Y, or there's another student in your school such that Y has a computer and X and Y are friends. Okay. So if we break that up, it's saying either X has a computer or Y has a computer and X and Y are friends. So in a simpler language, we're saying every student in your school either has a computer or is friends with somebody who has a computer, right? Either X has it or Y has it and X and Y are friends. Okay. Okay, so we had done this last time. I just wanted to do that again today. So did anyone have any questions on that? Okay. Again, you sort of have to just read it after you've written it down and break it down, sort of understand what it's saying, and then sort of rewrite it in a simpler language. Okay. Okay. Yeah, it doesn't have to be so elegant. It just has to make sense, and it has to not have variables. Those are the two things I'm looking for, really. Okay, if I ask you to translate a logic expression into an English sentence, just make sure it does not have variables. Okay, it should make sense and should not have variables. Okay. All right. So let's now move on. No, it doesn't have to be. It doesn't have to be perfect as that one. No. Okay. Okay. Let's move on. So we're now going to move on to section 1.6. Okay. So until now, we've basically discussed how to write sentences as logic expressions. We've discussed all different types of logic expressions, logic operators, logic symbols. Okay. We're now going to start moving towards proofs. Okay. So we're going to start with section 1.6, which deals with the rules of inference. Oh, somebody has a question. Yeah, sure. Go ahead.
I have a question for the statement of
Yeah.
the one that you made it into a simple statement, the one from before. Is it supposed to be every student in your school has a computer, or there is a student who has a friend who has a computer?
It's the same thing. Well,
because before you said there it's different from every, and then there exists.
Wait, how did you say it? Repeat it to me, the way you said it.
Like after the or, I said there is a student who has a friend who has a computer. Not every.
Oh, sorry. 1 second. No. I think I deleted it by mistake. Okay. All right. 1 second. Let me rewrite what I had. Can I bring it back? Nope. Okay. 1 moment. Okay. Give me 1 minute. Let me just rewrite down what I had, and then I'll try and clarify for you. Okay, so we had the sentence. Okay. Every student in your school has a computer. Or has a friend who has a computer. Okay, so the x is universally quantified. Okay, the y is existentially quantified. So I'm saying either x has a computer or he has a friend. There exists a friend that has a computer who's friends with x. Okay, so it's the friend that's existentially quantified one. All right, does that sort of make sense?
Yeah, I got it. Thank you.
Okay. Okay. All right. Okay, so rules of inference. Okay, so I was saying, any more questions on that, by the way, before we move on? Okay. All right. Okay, so we were saying that we're going to be moving on to proofs now. Before we do that, we're going to discuss the rules of inference. All right. We're going to discuss logical arguments. And the idea in this chapter is basically, if I tell you certain statements are true, what else can you infer is also true? So if I tell you, let's say 2 or 3 given statements are true, the idea is what can I infer is also to be true based on that, okay? So let me give you a couple of definitions, and then I will give you the rules of inference. Okay. So first definition, the first one here is for an argument. An argument in propositional logic is a sequence of propositions. Okay. All but the final proposition in the argument are called premises. And the final proposition itself is called the conclusion. Okay. An argument is valid if the truth of all its premises implies that the conclusion is true. Okay, so here's the definition, or a bunch of definitions here. All right, let me show you how we write this out. Okay. Let's say I tell you some proposition, P is true. And I also tell you some proposition, if P then Q is true. Okay, so here I have these 2 propositions. These are the first 2 in my sequence of propositions. Okay, I'm telling you both of these are true. Okay, all right. Now this symbol here basically means therefore, these 3 dots here. So if these 2 things are true, then I know that Q is true, therefore Q. Okay. So this here would be an argument in logic. Okay, I have a sequence of propositions. I'm telling you that the first 2 are true. I'm telling you P is true. I'm telling you if P then Q is true. Okay. What this argument is saying is that if the first 2 propositions, everything above the line is true, then we can conclude for sure that Q also has to be true. Okay. So therefore, Q is true. Okay, so this is how we write an argument. It's a sequence of propositions. The first 2 are the premises, P and if P then Q. The Q at the bottom is the conclusion. Okay, this argument is a valid argument here. Why? Because if P is true and if P then Q is true, then I know for sure Q has to be true. Okay. Why? Let's sort of break that down for a moment. P is true. Okay. If P then Q is also true. Well, if P is true and that's true, then I know the P here is true. So the only way that this conditional statement can be true is if Q is also true, right? Because if P is true and Q is false, then the implication here would have to be false. Okay, so the only way that if P then Q could be true when P is true is when Q is also true. All right? So this here would be a valid argument. This is a valid argument. Okay, all right. So we're saying, if I give you these two propositions, that P is true, and if P then Q I tell you is also true, we can infer from that that Q also has to be true. Okay. All right. Any questions on that? What do you mean? What's your question? Oh, yes. If the premises being, if the truth of the premises does not imply that the conclusion is true, right, then it would not be a valid argument. That's correct, right? So if for example, let's say I gave you if P then Q. Well, no, let me not do that. If P or Q, and therefore Q. Let's say I gave you this argument here, okay? So here I have, again, two premises. I can have more than two premises, by the way. Just in these two examples, I have only two premises. Okay, so here I have two premises. I'm telling you P is true, and P or Q is true. And I'm concluding, therefore, Q is true. This is not a valid argument, okay? Just because the first two propositions here are true doesn't mean Q is true. Okay, Q could still be false, and the premises would be true, okay? So this is not a valid argument. Okay. Just because P is true and P or Q is true does not mean Q has to be true. Okay? Q could still be false, and those two premises would be unaffected. They would still be true. Okay. Okay, so we cannot infer in this case. Just because the first two are true, we cannot infer that the conclusion is true. So that would not be a valid argument. Okay. Any other questions?
In the second example, are we inferring that P is true?
No. So in the second one, I'm telling you that P is true, and I'm telling you that P or Q is true. And I'm arguing that if those two are true, then Q also has to be true. But that's a false argument, right? Or it's what we call a fallacy. It's a false argument. It's not that that's not the case. Just because the first two statements are true, the Q does not have to be true. So this would not be a valid argument.
Got it. Thanks.
No problem. Any other questions? Okay. All right. Let me now give you a list of the rules of inference. Okay. So the rules of inference are basically a list of valid arguments. Okay. So rules of inference. So I'm going to give you now a table of valid arguments. These are all valid arguments. Okay. The first one, all right, is the one we already saw. Okay, so if you know that these two propositions are true, that P is true and P implies Q is true, you can conclude that Q has to be true. Okay. The second rule of inference is as follows. If I tell you the statement not Q is true, and I tell you that the statement if P then Q is true, you can conclude that the statement not P is true. Okay, let's sort of go through this one and see why this makes sense. I told you not Q is true. If not Q is true, then Q has to be false. Okay, if Q is false, then let's look at my conditional statement here. If Q is false, the only way that this statement can be true is if P is also false, right? Because if P is true and Q is false, then the statement is false, but I'm telling you it's a true statement. So the only way that can be true is if P is also false. If P is false, not P will be true, right? Not P has the opposite truth value of P. Okay. Not Q is true, right? When I write it out this way, let me erase this here. When I write this out this way, I'm saying this statement is true, and I'm saying this statement is true. And therefore, the conclusion is also true. Okay, so I'm saying not Q is true, and if not Q is true, that means Q is false. Okay. Okay. The third rule. Let's say I tell you that this statement is true, if P then Q. I have some conditional statement, I tell you that that statement is true. I have another conditional statement, if Q then R. Right? So this one is also true. So if both of these conditional statements are true, we can conclude that the conditional statement, if P then R, is also true. Okay. All right, and again, you can work through the logic and you'll see that that makes sense. Okay. Moving on to the next one. If I tell you the disjunction P or Q is true, I tell you that's a true statement. And I also tell you the statement not P is true. We can conclude that, well, if P or Q is a true statement, and if not P is a true statement, well, if not P is true, that means P is false. If P is false, the only way that the disjunction here will be true is if Q is true. So if these two statements are true, we can conclude that Q also has to be true. Okay. All right. Number 5. If I tell you a statement P is true, you can conclude the disjunction P or Q is true, right? As long as P is true, a disjunction of P with anything will be true. Okay. Disjunctions are true as long as one part is true. Number 6, if I tell you the conjunction P and Q is true, you can conclude that P is true, because the only way a conjunction is true is if everything is true. All its parts. All right, next. Let's say I tell you P is true and Q is true, then their conjunction has to be true, okay? These do have names. I'm not giving you the names because I'm not going to ask you to memorize the names. If you want, I can give them to you. Would you like me to give you the names? All right. Okay. You should know these rules, yes. Okay. Okay. The next rule of inference, this is the last one here. Oh, let's say I tell you the disjunction P or Q is true, and I tell you the disjunction not P or R is true. All right, you can conclude that Q or R also has to be true. Okay. All right, so those are the rules of inference. Okay. You can think of these rules, by the way, also as conditional statements. But let's not get into that. That might be that might be confusing. So let's just leave it like this, okay? So yeah, so these are all sort of, they should all make sense, right? These are logical deductions that we're making, that if this is true and this is true, therefore this must also be true, right? If A, B, C, and D are true, and then E must also be true. Okay. Okay. Any questions on any of these rules? You don't need to know the names. No, I didn't give you the names. I don't expect you to know the names. The names are all Latin words. Okay, just need to know the rules and how they work. All right. Okay. Ah, you learned the names in high school. Okay. All right. Yeah. All right. Yeah. Okay. All right. So those are the basic ideas. Okay. We're not going to do much with these rules of inference. I just wanted you to have them. Okay. I want to now move on to section 1.7. All right. I want to get into proofs. Okay. We're going to sort of be using them in 1.7 when we do proofs. Okay, in the proofs we're going to use them. All right. We might not state explicitly that we're using them. Sometimes it will be implicit, but the idea will be there. We'll be working in the background. Okay. Okay, so we're now going to move on to section 1.7, introduction to proofs. Okay. All right. So in this chapter, we're going to discuss how to do proofs. Some of you may have done proofs previously in geometry. What we're going to do is sort of similar to that, but very different at the same time. Okay, so we're going to discuss 3 different methods of proof in this chapter. All right, we're going to talk about direct proofs, and then 2 types of indirect proof. The first is going to be a proof by contraposition. And the last is going to be a proof by contradiction. Okay. All right. So in math, a lot of times we have mathematical statements that we want to prove are true. Okay. Any statement that we can prove is true is called a theorem. Okay. All right. So let's start with that definition. Okay. All right. So definition: a theorem is a statement that can be shown to be true. Okay. So in math, all the time we have theorems and their proofs. Right? A theorem is any statement that has a proof. Okay. All right. So we're going to discuss how to prove statements, mathematical statements. And we're going to start with direct proofs. Okay. And we're going to use direct proofs to prove mathematical statements that are conditional statements. Okay. All right. So let me give you the idea of it first, and then we'll write down what we're going to discuss. Let's say I give you a mathematical statement that's a conditional statement. Okay. I tell you if P, then Q. For example, let's say I tell you if n is even, then n squared is even. Something like that, right? Where n is some real number. Okay. All right. The idea is as follows. All right. This statement is a conditional statement. The only time a conditional statement can be false is when the hypothesis is true, but the conclusion is false. That's the only time that this thing can be false. Okay. So how do I show that this conditional statement is true? by showing that when P is true, Q also has to be true. Okay. If I can do that, then the statement can never be false, and it has to be a true statement. It would be a tautology, basically, right? It would always have to be true. Okay. So that's the idea of what we're going to do. We're going to show that when, to prove that a conditional statement is true, is always true, we're going to show that when P is true, the conclusion Q also has to be true. Okay. That's the idea of what we're going to do. So let's write that down. All right. Okay. So a direct proof shows that a conditional statement if P then Q is true by showing that if P is true, then Q must also be true. Okay. So that the combination P true and Q false never occurs. Okay. Okay. So a direct proof will have two steps always. Okay. The first step, we're going to assume that the hypothesis of the statement is true. You assume P is true. So there are two steps. Okay. First, assume the hypothesis P is true. Okay. Then you use whatever information you have in the background, all of your mathematical knowledge. Then use definitions, axioms. Right? Axioms are basically just statements that we accept to be true. Previously proven theorems. And the rules of inference. Okay. Use anything in the background, any knowledge that you have, anything you know to be true, to show that Q must also be true. Okay. All right. So again, to reiterate, what are we doing? We're going to be given a mathematical statement that's a conditional statement. And you're going to be asked to prove that this statement is true. How do you do it? So again, we said, if it's a conditional statement, there's only one case where it could be false. Okay. When P is true and Q is false, that would make it false. So we want to show that that can never happen, that that's impossible. So we have to show that when P is true, Q is also true. Okay, how do we do that? We start by assuming that P is true, show that when P is true, Q will also have to be true, and we do that using whatever mathematical knowledge we have. Okay. Any questions before we try an example? I think we have some comments here. Okay. Okay, any questions? Okay. Well, if P is false, then the statement is still true, right? The conditional statement will still be true. Okay. So we want to show, if you're asked to prove a statement is true, that means you're being asked to prove that it's always true, that it can never be false. Okay. All right. Okay. Any other questions? All right, let's try an example. Okay, so before I give you actually an example, let me give you a couple of definitions that we're going to be using. Okay, and these definitions will be helpful to us as we do the proofs. So first definition, this is for even and odd integers. Okay, so the integer n is even if there exists an integer k such that n equals to 2 times k. Okay, this is the definition of an even integer. It's even, a number is even if it has a factor of 2. Okay, if there exists an integer k, such that n equals 2 times k. N is odd if there exists an integer k such that n equals to what? Does anyone know the definition for odd integer?
2k plus 1.
Yep, exactly. Okay. Now every integer has to either be either even or odd. So if it's not one, it's the other. Okay. All right. Next definition. Oh, okay. I see we have some confusion here. 10 is 10 even. Yes. Why? Because I can write it as 2 times another integer. 2 times 5. That's my n, that's my k. 12 is even. Why? Because I can write it as 2 times an integer. 0 is even because I can write it as 2 times an integer. 100 is even because I can write it as 2 times an integer. And so on and so forth. So here, this is the n. This here is the k. N, k, n, k. Right. What about odd? An integer is odd if I can write it as 2 times an integer plus 1. So 3 is odd because I can write it as 2 times 1 plus 1. That's n, that's k. 11 is odd. I can write it as 2 times 5 plus 1. That's n, that's k. Okay? And so on and so forth. Okay, does that help? Yeah? Okay, great. Okay. Sorry. All right, let's now move on to our next definition. An integer, remember integers are whole numbers, okay? An integer a is a perfect square if there is an integer b such that a equals b squared. Okay, so what would be some examples of perfect squares? 9 is a perfect square because I can write as being 3 squared. 16 is a perfect square, that's 4 squared. 25 is a perfect square, that's 5 squared. 36 is a perfect square, that's 6 squared, and so on and so forth. Okay. That's the A, that's the B, and so on and so forth. Any questions on that definition? All right. One more definition. All right, a definition for rational and irrational numbers. The real number r is rational if there exists integers p and q with q not equal to 0. P can be 0, but q is not equal to 0, such that r equals p over q. Okay. So in other words, a real number r is rational if I can write it as being equal to one integer divided by another integer where the denominator is not 0. Okay. A real number that is not rational, that cannot be written as a fraction or a ratio of two integers, is called irrational. So a real number that is not rational is called irrational. Okay, so any real number that cannot be written as a ratio of two integers is called irrational. All right, so for example, 2 over 3 is rational. It's one integer over another, right? It's p over q. 10 is rational because I can write it as 10 over 1, one integer divided by another. Okay, and so on and so forth. Okay. Any questions so far on that? An example of an irrational number. Oh, well, we'll get to those soon. But irrational numbers would include, so those are rational. What are some examples of irrational numbers? Well, pi is irrational, the square root of 2 is irrational, the square root of 3 is irrational, and so on and so forth. Okay, like, so none of those numbers can be written as a ratio of integers, as one whole number divided by another. Okay. Yeah. Well, we'll see a little bit more when we get to that. All right, we're gonna prove that the square root of 2 is irrational. Okay. So how does it play with p and q? Because I cannot write it as one integer divided by another. Right? P and q are two integers. Okay. The square root of 2 cannot be written. It is not equal to one integer divided by another integer. Okay. Okay. All right. So let's now, with all these definitions, let's see an actual example of a direct proof. Okay. Let's say I ask you to give a direct proof of the theorem if n is an odd integer, then n squared is odd. So here is our statement that we want to prove. It's a conditional statement. I've written it out so that you can see it's a conditional statement. It's not always clearly written out as a conditional statement. Okay, but we'll start with this. Okay. If n is an odd integer, then n squared is odd. Okay, so what's our hypothesis here? Our hypothesis is that n is odd. The conclusion is that n squared is odd. Okay. Okay. So that's our hypothesis. That's our conclusion. If p, then q. Okay. We want to prove that this statement is true, that whenever n is odd, n squared is odd, using a direct proof. So step 1. We have to show that this thing can never be false. So we're going to show that when p is true, q will also be true. Step 1, assume p is true. Assume p is true. Okay, so what is p? P is the statement that n is odd. So we're going to assume that n is odd. Okay, we're starting with that assumption. Okay, let's write out what that means based on the definition. If n is odd, based on the definition, we can write n equals to 2k plus 1, where, so all right, then n equals, well, then n equals 2k plus 1, where k is an integer. Okay, so this is what we have so far. We're assuming the hypothesis is true. So that means we're assuming n is odd. By definition, n equals to 2k plus 1, where k is an integer. Okay. Any questions on the first step? Okay. So we're only looking at where p is true. Now we want to show in our second step that when p is true, q also has to be true. So step 2. Okay. Using the above assumption, show that the conclusion Q is also true, or must also be true. Let me put it that way. Okay. Okay. So I'm just going to rewrite n equals to 2k plus 1, which is what we had from step 1. Okay. So we're assuming that n equals to 2k plus 1. We're assuming that that is true. We want to show, if you look back at the original theorem here, the original statement, we want to show that n squared is odd. Okay, so we want to go from n to n squared. We want to go from n to n squared. So how do I do that? I'm going to square both sides. I'm going to take n equals 2k plus 1 and square both sides. And that way I'll find out what n squared equals to. Okay, so square both sides. And we get n squared equals 2k plus 1 squared. Okay. So the reason I'm doing this is because I'm taking what I have for n, and I want to find out what n squared is. What is it equal to? And is that odd or is that even? Okay. So let's expand the right-hand side here. 2k plus 1 squared, if I expand that, that's 2k plus 1 times 2k plus 1. That's equal to 4k squared plus 4k plus 1, right? Distribute, FOIL, whatever you want to call it. Okay, so n squared equals this thing. N squared equals 4k squared plus 4k plus 1. Is that odd or is that even? We want to show that that is odd, right? That's our goal. We want to show that q is true, so we need to show n squared is odd. Okay, how do I show 4k squared plus 4k plus 1 is odd? So you have to show that n squared equals 4k squared plus 4k plus 1 is odd. That's what we want to show. That's what we want to conclude. Okay, if that's odd, then the conclusion is true. All right, so how do we do that? We always have to go back to the definition. So for this to be odd, I have to be able to write it as 2 times an integer plus 1. Okay, that's the definition of odd. So for this to be odd, I have to rewrite it as 2 times an integer plus 1. I can do that. I can take 4k squared plus 4k plus 1. I can factor out a 2 from the first two terms, so that it equals to 2 times 2k squared plus 2k plus 1. Okay. If k is an integer, if k is a whole number, which that was our assumption at the beginning, right? K is an integer. Okay, we know that I take an integer, if I multiply it by other whole numbers and add it together with other whole numbers, I'm going to end up with a whole number. I'm going to end up with another integer. So this here, everything in the parentheses here, that's an integer. Okay, so n squared is equal to 2 times an integer plus 1. By definition, n squared is odd. By definition, n squared is odd. Okay. So if we assume that n is odd, we just showed that n squared also has to be odd. So the proof is now done. We've showed when n is odd, n squared has to be odd. Okay, so the proof is complete. Okay, sometimes you see in the books they put a little box at the end when a proof is done. Okay. Okay, so those are the steps of the proof. Let's take comments and questions now. Okay, any comments? I'm not sure I followed the comments here, so if you have a question you want to ask now, go ahead. Right. 2k squared plus 2k is an integer. Why? Because k is an integer. Remember, what does integer mean again? It's its whole number. K is a whole number. If I take a whole number, I square it, it'll be a whole number, right? K squared. I multiply it by 2, it will still be a whole number. I add 2 times k, it will still be a whole number. So this thing here will be an integer, okay? If k is an integer, that will be an integer. Okay. Yeah, can be any number, okay? Something is odd if it's equal to 2 times a whole number plus 1. Okay, it doesn't matter what that thing is. As long as it's 2 times a whole number plus 1, it's odd. Okay, any other questions? Okay, all right, so the proof is complete. Why? Because we demonstrated, again, just to reiterate, we demonstrated that when p is true, q has to be true, right? When n is odd, we showed n squared has to also be odd. And therefore, the statement can never be false. It always has to be true. So the statement is always true. Yeah, if k is an integer, then 2k squared plus 2k will also be an integer. Okay. Right. That's always true. That's something that you can use just from your general knowledge. Okay. If you take a whole number, like I said, if you add whole numbers together or you multiply whole numbers together, you're going to get whole numbers. The only way that you could turn a whole number into, let's say, not a whole number, let's say a fraction, using one of the 4 operations, is to divide. Right. So if I took k and divided by 3, if k is a whole number, k divided by 3 may or may not be a whole number. Right. But if I multiply k by something, it will be a whole number, or if I add something to it, it will be a whole number. Okay.
Sir, I had a question.
Yes, go ahead.
So, sir, this is a conditional statement in Q, right?
If p, then q, yes.
But we know in the truth table of conditional statements, if P is false and Q is the value, whatever the value of Q, the statement is still true, right?
Yes.
So so why do we have to assume that P is true? Like, because the value of P does not matter.
Okay, good. Okay, so let's go over that for a moment. Okay, let's go back to that for a second. Let's look back at the truth table here for conditional statements. Okay. All right, this was the truth table for the conditional statement if p then q. Okay. The only time that this statement can be false is in this case here. Okay, when p is true and q is false. What you're being asked to do in these proofs is to prove that this conditional statement is always true. Okay, so you have to show that this second case here cannot happen. It does not occur. All right. So that's what we're doing. We're showing that this thing here does not happen, because when p is true, we're showing that the q also has to be true. Okay, so that's what we're doing. We're sort of eliminating this case. We're showing it can't be, it cannot exist in this particular problem, and therefore the statement is always true. Okay.
I understand, sir. That's very clear. Thank you.
Okay, no problem. If that's the case, that would make yes. If you took an integer and divided by another number, you could. It's no longer necessarily an integer. Okay, and that could create issues for you. Shoei was asking, how do you indicate that that's odd to the proofreader? How do you point? Oh, again, you can assume that you're writing for me. You're writing for somebody that knows the definition. Okay, so once you've shown that it fits into the definition, you can say by the definition of odd, this thing is odd. Okay, once you show it's 2 times something plus 1, you say, oh, that's the definition of an odd integer, so this thing is odd. Okay. Does that answer your question? Okay. Okay. All right. All right. Let's only for now take questions that apply to this. Okay. All right. Any other questions about this? Okay. Let's maybe do one more together. We have some time still. Let's try the following. All right. Show that if m and n are both perfect squares, then n times m, their product, is also a perfect square. Okay. Okay, so again, this is asking you to basically to do a proof. Show that this statement is true. Okay, show that if m and n are both perfect squares, then n times m is also a perfect square. Okay. So we have here, I'll just put quotes around the conditional statement that we're trying to prove. Our hypothesis is the statement m and n are both perfect squares. That's our P. The conclusion is that their product is also a perfect square. That'll be the Q. Okay. Okay, so we're going to do the same thing. We're going to start by assuming the hypothesis is true. Okay, so assume that m and n are both perfect squares. Okay. And let's write down what that means based on the definition. So based on the definition of perfect square, that means I can write m equals to s squared and n equals to t squared for some integers s and t. Okay. Okay. So everyone with me so far on this problem? Okay. All right. So now we move on to the next step, step 2. Okay. We need to show that their Q, the conclusion, is also true. So show that the conclusion is true. So show that the product n times m is also a perfect square. Okay. So again, we start with our first step, our step 1. We start with the information that we have. We know m equals s squared, n equals t squared. We want to show that their product is a perfect square. So we're going to write n times m, which is based on step 1, n is t squared, m is s squared. So our n times n will be t squared times s squared. Based on the rules of exponents, I can rewrite this as t times s squared. Okay. So n times m equals to t times s. T and s were both integers, right? T and s were integers. So an integer times an integer is an integer. This is an integer. So ts is an integer. So n times m equals to an integer squared. Based on the definition of a perfect square, n times m is now a perfect square. It equals to some whole number squared. It's a perfect square. So by the definition of perfect square, n times m is a perfect square. Okay. And we're done. I'll put a little box there. Okay. So we've shown that the conclusion is true, that when n is a perfect square and m is a perfect square, the product will also be a perfect square. It will be some integer squared. Questions on this problem? Can I scroll up to the question again? Yeah, let me scroll up for just a moment and I'll scroll back down in a second. Well, here, let me just do this. There. Will we always assume that what we are proving is true? Yes, unless the problem asks you to prove the statement is true or false, in which case you sort of have to figure that out yourself. But most of the time, I'll give you a statement that's true and ask you to prove that it's true. Oh, and it not be a perfect square. That's exactly the point. We're proving that it's always a perfect square. Okay. Okay. Are we dismissed? All right. Let's. Any final questions before we finish for today? All right. Let's take attendance. Everyone, just let me know you were here, and you can go, and I'll get you guys some homework as well to practice. Okay. Okay, everybody. I assume I got everybody. I'm gonna head out. Take care. Have a good day.